Hi, this video is a revision aid for computing fundamentals. So I'm going to start with binary, or should I say number systems, and remind you about the hundreds, tens and units for representing, say, 101. So 100, no tens and 1 unit. I'm going to then show you the base 2 variation, so that's 2 to the power of 1. Same thing here, so this is 10 to the power of 0, 10 to the power of 1, 10 to the power of 2. I'm going to just quickly remind you of this, and you would show all of this. You could even show what it means underneath, because this is your working out. 64. And then, so for example, if you wanted to reference, or sorry, to show 42, it would be 32 plus 10 with the other set to 0, so that would be 42. If you wanted to show what, say, 1, 2, 3, 2, 3, 4, 5, 6, 7, 8 is, you would show this as an ASCII value if that's what was wanted. So you might be asked to represent this in ASCII and say what letter it is if you were given the ASCII table like this. And so that would be, again, looking at this, it'd be 1, 2, 4, 8, 16, 32, and we don't need to worry about those. So 32 plus 16, 48, plus 4, 52, 53, so that's 53, and that would be 53, which is the number 5, so 5, and that's represented as an ASCII character. Don't forget to differentiate between integers and ASCII, so you could show how 5 and 5 as an integer are different. So you might want to show that, show how 5 and 5 are different, for example. That's a good one. So 5 as an ASCII and 5 as an integer. So as ASCII, 5 is, like I said, 53, and we already know what that is, 110101. So 110101, we just check correct. But as an integer, that's not the case. It'll be 1, no 2s and 4, and then the rest would be set to 0s. So this is 5 as an int, and this is 5 ASCII as 53. So that's a good sort of question to clearly show, and you might want to show the workings out as said. So you could put the 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, and what they mean as well. So that's a binary representation example. So another one that you might want to revise is how to represent hex. This is often used to represent a colour. So you could come up with a colour, so RGB, how to represent purple, and what you would do in hex is you want to set the R, a G and the B, and you want to set this could be something between, say, 128, 255, so red and blue all the way to 255, so 128 in hex, or you could just go all the way full red, full blue, and that would be FF, 0 FF. Then you could explain that it's 0 to F, which is 0 to 9, A, B, C, D, E, F, where this is 15 and this is 10, 11, 12, 13, 14, 15. So 15 times 16, that's the max value. So you could explain how that relates to base 16, or that is base 16, where you have 0 to 15 possible values. So just understand hex and how it works in case you get a small question on that as well. It could be that you might be asked a question on setting security. So back to binary, it might be that you need to set the permissions for a file to RWX, RX, R, using the chmod command. So using the binary representation. So using the chmod command, what would the values be using the binary representation? So the binary method. And again, you can show that an R would be 4, a W would be 2, and an X would be 1. And that's for the owner. And for the group, it's the same. So 4, 2, 1. And for the world, it's RWX 4, 2, 1. And in this case here, so file 1 would be 4 plus 2 plus 1. 4 plus 2 plus 1, show the workings out. So that's 7. R and X would be 4 plus 1, which is 5. And R on its own. So 754. Chmod 754. File 1. That's what that is. So that's how you would use the binary method for working out and setting permissions for this file based on this permission structure. So then we have some more questions, quite simple questions that you should be able to answer using the not operator on the following data. So the output would be to reverse it. Now you're unlikely to get a question on that unless you're doing a GCSE or below, but it's just reversing, so it's the complement of the value. The opposite. Oops. 1, 1. And use the XOR operator, so you should be able to do this where you're XORing these together. So remember, with exclusive OR, it's one or the other, but not both. So that would be a 0. One or the other, yes, but not both. Nope. No, no, yes, no. So it'd be true as long as it's just one or the other, but not both. Same here. No, yes, no, no, yes, 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 no. So that's the answer for that one. It's just a case of practicing so that you know how to do these. So using the AND operator. So remember, the AND operator is where you both have to be set. So we're going to AND these together using logical AND operator. So both of these need to be set in order for it to be true, otherwise it's false. So 1, 0, 0, 1, 1, 0, 0, 0 when you've ANDed these two values together. Again, I'll do this one. So that's 1, 0, 0, 1, both have to be true. 0, 0, 0, 0. That's the answer to that one. Now using the OR operator, it can be one or the other and both. So that'll be 1, 1, 0, both. Yep, both. No, one or the other, that's fine. So that's the OR operator. Just write down as many of these as you can. Write down quizzes for yourself to do later. Make your own little worksheets like this if you need to practice this. Okay, so give an example of when the not operator might be used? Well, this would be in 2's complement, which will be shown shortly, for negatives, negative numbers. And you can give, you would normally show that as an example, so where you actually use the sign, the first bit for the sign. So if you wanted to represent minus 42, you would show this where it has a 1 at the beginning. So you give an example of how to do 2's complement. I'm not going to show that on here, I'll do that in a moment. Now the AND operator can be used to mask bits. So it could be an IP address with the network mask just to pull out the subnet mask. So it could be 192.168.10.2 with a net ID of 255.255, and then, whoops, sorry, it's just moved itself. Let me put that down again. .00, and when you AND these together, that's like saying 111.111.00 with 192. So obviously it'll be more ones than that, but just imagine. So that's because it's an AND, that's going to come out the same value. And because that's an AND, that's going to come out the same value, whatever it was. But these are going to be set to 0. So that will give us, oh, it's done it again. That will give us the network address, which is 192.168. So for this is driving me mad. For this, we need to make sure that we give a good example, and IP addressing is a nice example. Right, the next one, let's hope it doesn't move down, is masking the leftmost 4 bits of a bit pattern using AND to set them to 0. So we'll have a bit pattern. Alright, and to set them to 0 by using AND, if we put 0 underneath them, this is quite tricky because it keeps moving this file. If we put them to 0, then it will definitely get rid of them from the equation, leaving us with just this, because when you AND that with a 0, it's a 0. Anything with a 0, it's a 0. Fiddly using this document. Whereas that will remain the same as what it was before. So that's taken away the first 4 bits. Show an example of how OR can be used to set the leftmost 4 bits to a 1. So OR can be used to set the leftmost 4 bits to a 1 by having a 1 there, and whatever they were before, well, that doesn't matter because using OR, that will force these values to be a 1, and because one or the other or both, and then this will be whatever it was before. So that forces those all to a 1, which could be used for image processing. Now I'll show an example of a left shift operation on 8 bits. So just show an example, any example, sorry about this interface, just move them to the left. For example, left 1, we'll just move everything across. So that's gone. So let's put that there. 0, 1, 1, 1, 1, 0, 0, 0. So that's all gone to the left by 1. Present the results in decimal for the input and the output. Well, this is where you're going to show the multiply by 2 when you shift it by 1. So this is going to show how it actually multiplies the value by 2. So show this as a decimal value. And then just another example here. So using 8 bits, I'll give myself a very, very simple 8 bits value here just to keep my life easy. So 1, 2, so that's 12. So 8 and 4. Or was that 4 and 2? Oh, that's 6, sorry, 6. So when you move them across, you get this. And that's 8 and 4, so that's 12. So it's multiplied by 2. Hopefully that makes sense. So that's showing an example of multiplying. And then this is obviously going to ask you to show an example where there's a right shift. So let me do this one quite easily as well. So that's 1, 2, 4, 8, 16, so that's 32. And when we right shift, it will be there, which makes it 16. So that shows how it's divided by 2. And there's a further example. Let's do a slightly bigger number, keeping it simple, 64. And then if we right shift it, it's 32. Oh, here we go. It's 32. So you can see it's divided by 2 there as well. Right, so comment on the use of the left. So left multiplies. So left multiplies the value by 2 when shifted left by 1 digit. Same here. Divides the value by 2 when shifted. Whoops. Oh gosh. When shifted right by 1 digit. Okay, so that's a comment. Another thing that you can do with your ANDing is to show how shifting and can show whether a particular bit pattern is a 0 or a 1. It might be that you have, say, 4 sensors and you're using bits to represent the status of the sensors. So it might be that sensor 1, 2 is on, 3 is off, and 4 is on. If you use AND, then that can mask values out and shift. So if we wanted to see whether sensor 3, 1, 2, 3 is on or off, what we can do is use AND. So making sure we use the AND operator there. We can shift right our third bit 3 times, so it ends up being here, and that's there and that's there. It doesn't matter because we're now just looking at this one and we're ANDing it with this. So we're ANDing it. The result is 0, so we know it's off. Had it been set to 1, the result would have been 1, and it would have been on. So you can give that as an example. You can pick any example like that. It's not necessarily sensors, it can be all sort of other data that you might be manipulating. So another question is to show integer overflow. show an example of this. You don't need to use a full 16-bit. You can just say, using just 8 bits as an example to keep it simple, just for simplicity's sake. Okay, we know that 8 bits is not an integer, so to do that you can write your binary at the top just to keep it simple, and that is your 2 to the power of 0, 2 to the power of 1, 2, 3, 4, 5, 2 to the power of 7. And to keep the number so that you can show overflow, what you want it to do is choose a number that is going to be quite large. That's when added together with another number, it's going to overflow, so you haven't got enough bits to store the answer. So your answer is not going to be able to store it. So for example, if all you have are these bits and you add these two values together, it's very easy, because you just need to say, well, anything over 8 added to this will cause overflow. So just adding anything over 8, like this for example, will cause overflow, because that's going to be 255 take away 8, which is 247 plus 16 is clearly going to be over what we are able to represent with this, which is 255, 0 to 255, and that's over 255. So just show the answer being bigger than what can be represented. So the answer is greater than what can be represented. Obviously, if 16 bits, it'd be no different. It'd just be a much larger number to work with. So you don't really need to. You can just explain that you are aware that there are 16 or 32 bits, but you're going to show using 8 bits for simplicity's sake. Show it in the binary formats like this, and that way it can be easily seen. So a good way of showing this is to just leave one of these and say, well, if you add a number that's slightly bigger than that, you clearly are going to go over, and that's going to create overflow. So that's overflow. Right, so another area to concentrate on is dealing with negative numbers. So 2's complement and the storage of signed ints. Again, they are 16 bits, but I'm going to work with 8. So for simplicity, again, you would make this clear using 8 bits. So one of them will be for the sign. So I'm going to write down 7 bits worth of data like this, and then this one's going to be for the sign, and show this using 2's complement. So if it's a minus, it's going to be 1, 2, 4, 8, 16, 32, 64. So this is 64 plus 16, 88. So this is 90 minus 90. So show minus 90 represented and show 90 represented. So this would be 90, and the way in which you'd represent minus 90 would be to write the bits, but obviously because we have a minus, it would be copy all of the bits until you get to a 1, and then flip the rest of the bits, and you will see that the last bit is flipped to a 1, and that means it is minus 90. Okay, so that's 2's complement. So 1, and then when retrieving, so you could explain that when you retrieve the data, if this bit here, if that's 1, then perform 2's complement. Okay, so you'll reverse the bits. So it'll be 0, 1, 0, 1. And it's basically the reverse until you get to the first one again. So it's going to be 0 and then 1, 0. And that will give you back your 90, and then you add the sign to it as well. So if there was a 1 there, you convert it back, which gets you back to the original value, as can be seen up here, and then you add the sign. So that's 2's complement. I'll just do that again actually to help you out. So just cleared the screen. Let's work with 42 and minus 42. Using our binary 1, 2, 4, 8, 16, 32, 64, and then this is the sign. So call that S for sign. So it's 0. So for 42 itself, it will just be 1 with these set to 0, so that's 42. But for minus 42, it will be 0, 1, 0, 1, 0, 1, 0, and obviously that's 0. And then there will be copied, flipped. So you copy until you reach 1, and then you flip the rest, and then that becomes your indicator. And then for the retrieval, so in the case of this one, oops, let me just fix that. So in the case of this one, because it's a 0 here, then leave as is. But because this is a 1, do 2's complement, which means copy all the bits until 1 is reached and flip again. So 0 and 0, and then add the sign. So you have your 42 and you add the sign. So that's 2's complement, and that's how signs are represented. So you do lose the final bit. That's how computers perform the storing of integers. Another area that's related is your Huffman coding. So pick a sentence and draw the tree and show what the code would be. So the whole question here is to show the code as well as the ASCII. So the ASCII plus the compressed version. Oh, here we go. Contessa's trying to be helpful to me. Let's ignore that. So we'll use a phrase. So pick any old phrase with multiple letters that occur frequently. Let me think of one. So I see the sea, just to help me out here. What you do is you write down ISETHA, and they're all of the letters. How many times? It occurs 1 time. S occurs 2 times. E occurs 4 times. So you write in the frequency of the letters, if you remember. T occurs 1 time. H occurs 1 time. And A occurs 1 time. And then you write these in order. So A1, I1, H1 and T1, and then we have an S, it's a nice easy example, and an E. So we put these in order and we start to build the tree, and that's a 2 to find our A and I. remembering it's a binary tree, so we have to use just 2 branches per node, so that's TH, and we can join these together to make a THIA node, which comes up to 4, and then we join these together to get 6, which is for E's and S's, and we've already got a branch going on onto there, so what we need to do now is join these together to get our final 10, which will give us access to ES, TH, I, A, all of these letters. So this is the parent, or the root node of the tree. These are the branches, and then what we do is we use binary to label up our branches. So we have a 0 or 1, we'll use 0 for the left, 1 for the right, 0 for the left, 1 for the right, be consistent. And then what we do is we show the code. So for E it's 0, 0. For S it's 0, 1. For I it's 1, 1, 0. For T it is 1, 0, 0. For H it's 1, 0, 1. And for A it's 1, 1, 1. Again, no ambiguity here. And so you can write I see the C in ASCII, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 times 8. And what you would do here is that would be represented as 2 bits. That would be represented as 3 bits. E's are represented using 2 bits, so 2 and 2. T is represented using 3. H is represented using 3. E is represented using 2. S using 2. E using 2. And A using 4. Add those up. So that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 21, 25. So 25 bits instead of 13 times 8. So that's 80 plus 104. So it's about a quarter. So compression for I see the C using Huffman coding. In comparison to the ASCII representation, you might want to show the ASCII representation for it. That'll make it a lot better as an answer. So remember the rules to write down a sentence that has plenty of frequently occurring letters. Write down the table of all the letters. Make sure they match up so you can see that there are, say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I have forgotten the space actually, I do that. So that actually should be 1, 2, 3. That should have been joined up, but let's just imagine there's no spaces in my example just to help me out a little bit here. But you would normally put the space in there as well. So excluding the spaces, you can still see a reasonable compression rate, and actually the spaces are more frequently occurring, so they'd be along over here anyway. Okay, so let's do another example of that as well to help you out. Okay, I'll give you another example. I'm going to use a simple phrase. It might not be the exact one that you're familiar with. A cat sat on a mat. I want to make sure there's a reasonable frequency here. I'm going to remember the spaces this time, so don't forget those. So we have A, C, T, I forgot the space already, S, O, N, M. I think that's it. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And so we need to make sure that the frequencies add up. So we have 1, 2, 3, 5 A's. We have 1 C, 1, 2, 3 T's, 1, 2, 3, 4, 5 spaces. So these are the most frequent. S, we have just one O, 1 N, and 1 M. So this is our frequency table. Now we list those at the bottom. So that will be M, N, O, S, C, and then we have a T. So I'm listing these in order, remember. This is revision, so A and space. So that should be good. So let's just add these up to make sure they equate. So that's 14, 15, 16, 17, 18. So that's correct. And make sure we label these up here. There's lots of ones, which is quite helpful. A T is 3, and that's a 5, and that's a 5. So again, 18 times 8, 80, 60, 144 possible bits. And in this case, we will create our binary tree again. That gives us the 2 for N and M. That gives us 2 for SO. That gives us 4 for SONM. Once you've done a few of these, you'll get quite quick. Remember, it's a binary tree, so we only have 2 branches per node. So this now is TCSONM, and that adds up to 8. And we still have 10 to go, and that gives us these 2 here. So there's 10. So just these 2 nodes here are providing us with 10 of the values, which is quite good. You can already see a decent compression with this. So let's label it up. Our binary tree has 0, 1, 0, 1. Be consistent. 0 on the left, 1 on the right, 0, 1, all the way across. And this gives us our code. So an A is going to be 0, 1. A C is going to be 1, 0, 1, 1, 0, 1. A T is going to be 1, 0, 0. The space is 0, 0 in this case. The S is 1, 1, 0, 0. The letter O is 1, 1, 0, 1. The N is 1, 1, 1, 0. And that's it. So a cat sat on a mat is 01 with the space, which is 0, 0. Cat 101 with the 0, 0. T 11100. So A, I think I've, oh yeah, this is the space, isn't it? Cat, a cat. So this is A, so I did that wrong then. And then T is 100, and then it carries on from there. But the frequency of that will be 2 bits. So 2 bits for that, 3 bits for that, 2 bits for that, 2 for A, yeah, 3 for T, that's correct, and 2 for that, 2 for that. S is 4, A is 2, T is 3, so it's the number of bits to represent it. 2 for a space, 4, 4, 2 for a space, 2 for an A, 2 for a space, M is a 1, 2 for an A, and T is a 3. How many bits? So that's 4, 7, 8, 9, 10, 11, 12, 13, 14, 18, 20, 23, 25, 29, 33, 35, 37, 39, 45. So 45 as opposed to 144. Again, it always ends up to be around about a third. It just does. It's for the English language because of the high frequency of letters that you'll often find. So that's another example of Huffman coding. That's what you would need to do for that type of exam question. Okay, so on to another area now, and we have file management. We have operating systems. Sorry, I should have introduced it better. We have file management, memory, process, and device. So we're going to look at OSs. A typical question would be to compare or explain what each of these do. In terms of operating systems, you might want to use your common sense here and think, well, the operating system is certainly going to need to allow you to access your files. So access to files via a GUI or command line or the user interface. Let me just write those again. So in terms of operating systems, access to your file, security, so against your profile, user profile, so that's got to be matched up with the file. Mention the permission blocks of different operating systems. So the permission structure. You can give an example of Unix where you have your read write X, read write X, read write X blocks. You can explain this in some detail. And then there's the loading of the file into memory if it can fit it, otherwise you've got your virtual memory. And there's the managing the file, making sure the file can be read. Then there are other issues. For example, you have naming of files, so being able to copy, delete, and just basically do administration of files. So the operating system needs to allow for all of that, as well as links, e.g. shortcuts or symbolic links. So there's all of this stuff for file management, quite a lot there. Let me just try and get rid of all of this. And so that's the sort of thing you need to talk about for files. In terms of memory, let me make this a bit thicker. You have your virtual memory, you have the physical, and the operating system needs to swap data and processes into and out of VM and manage it. So it's using the RAM plus disk. So discuss that, do some research and write some sentences on that. That's all it is. And then in terms of process management, you can discuss that the operating system needs to load a file into memory, which is the program code, which it could be executable, binary, etc. So that needs to be scheduled So schedule the jobs. So queue tasks for I/O. Move it into and out of CPU. So the operating system needs to do all of these things, as well as manage open files, etc. So there are other resources as well. So it needs to manage process resources. This is the sort of thing that you would write about. A nice sentence in your own words, using some examples on how processes are dealt with. Certainly don't want to write answers that are paragraphs from textbooks that have been memorized. It's often better to explain this yourself to show a clear understanding. Device management, well, you have your I/O devices, you have your internal components, and there are device drivers to worry about. So the operating system needs to convert that to the hardware abstraction layer, for example, in Windows, and it has to interact with the kernel. So just discuss the issues of working with different types of I/O, so different peripherals. You might have, say, or even different versions as well, e.g. 2 printers. Okay, so hopefully that helps you with what to write for your operating systems. So finally, let's cover networking. You might be asked about protocol. Nice example for that is to show communication between people and how there tends to be a social etiquette, a way of communicating. You could use this sort of sequence diagram, so person 1, person 2, that's the standard way of talking. Hi, hi, how are you? If you were to do things more representative of how you would represent them in networking, fine, how are you? Then you might it might be better for you because you're showing an understanding of how to represent protocol, and then you could show this in terms of a computer system as well. So let me just show you that in terms of how you'd represent it if it was a computer in terms of protocol. Oh, this is a pain, but I'll take my time. And if it was a computer, so computer 1, comp 2, it might be that they send connect, and then this one might say, yep, I acknowledge your connect, and then this one might say request data, and this one might say ack request, things like that, and then it might send the actual data. So you can show this as a protocol and then mention about things like TCP/IP being a standard way of communicating. You could mention the OSI model if required as well. So something about routers and bridges. If you were asked questions about those things, let me just get rid of all of this. So the different devices that you might have to connect on the network. So switch or bridge, a router, and then you could explain that this router works at the 3 layers, and this is 2 layers, and you could explain that this is to connect LANs, isolate traffic, but it works with MAC addresses, so it doesn't deal with aliases, no sort of host IP address dealt with. Alright, with a switch, in terms of with a router, then it does IP addressing and finding quickest path, and is for a wider area network solution. So this could be just local networks, things like that. A brief comparison between the two. Another question that you could be asked is to give examples of client and server. So give examples of client and server solutions. So client, server. You could say your browser, which connects via the HTTP protocol to a web server running at port 80. You could have DHCP. I need to find out what they are. DHCP Client. So this is going to give back HTML and JavaScript. HTML5, for example. DHCP Client, connect to DHCP server. This will give back an IP, so request, and this one's going to request to the DNS server, and that will send back an IP. So you can give examples of these three things here. A bit messy, so I will clear that up. But what you want to do is explain them. So don't just use diagrams. Don't just write sentences. Diagrams are a lot better. So in your DHCP example, you are requesting for an IP address. You are getting this from your server, and this could be from the ISP. This could be your home PC. So just give detail. It shows understanding. And this is the DHCP server, and this will give you back an IP address, which you can then use. So write all of that as well as giving a diagram to show the communication between the two client and server systems, and do that for 3 examples. All right. As for TCP/IP, you might want to show how that fits onto this 7-layer model. So label that up. So you wouldn't need to memorize, because that's not really a very good question, but you might want to show that you have, say, FTP, HTTP, Telnet, etc. as your apps, and then you've got your TCP UDP optionality, whether you want to have connection or connection less, and then you have so that's your transport layer, and then you have your network layer, which is the IP, so it's your routing and your IP addressing. So you've got your ARP, RARP, etc. for that, and then you have the data layer, which is your error control and your MAC, medium access control, so e.g. your Ethernet, and then the physical. So physical, the medium, and that's your TCP IP stack. So a nice little summary with sentences. Show it in context, show it with examples, and you could maybe show it with the two sides communicating. And that's your networking really. So I think that pretty much covers most of it. And so the last area is security, where you might explain 3 ways of your system becoming vulnerable. So you could pick from things like snooping, masquerading or modification of data. Modification, these are masquerading. We covered these. Somebody snooping into what you're doing, so connected to your Wi-Fi, looking at what you're doing. Something modifying your data as it's being transmitted for their own benefit. Something acting as yourself. So have a little look at the ways in which your systems can be vulnerable, made vulnerable, your data being accessible. So that's something to look at. There are others like denial of service, repudiation, replaying, so asking for the same thing to be done again because it hasn't been done, repudiation, and denial of service. So look those up and you might be asked to explain those. So an example of a mono-alphabetic cipher, for example. What is that? That just could be, for example, where the letters of the alphabet are exchanged with, say, the next one. So quite a simple exchange. So that's what you need to do for that. And the need for digital signatures. So a final area is the use of digital signatures to allow users to feel safe and trust your site. And why do we need X509? Because we need some sort of a standard. So go ahead and look those up. And again, it is just a case of explaining these things in more detail. So why do we need a digital signature? Well, just like you would sign for anything. So just so that you can get some sort of feeling of trust for the data that you are about to access, the website that you're going to access, to make sure that it has been signed and authorized. And so you can trust the website, and so others can trust your website. And why do we need X509? So a quick overview of X509 certificates. They contain the version of the certificate, serial number to identify the certificate, and information like algorithm information used, the issuer's name, so who authorized it, how the validity period, date, start and end date, the name that the certificate is issued to, public key information, and extra information like that. So it's a standard document that allows people to use the SSL secure sockets layer in order to access your servers and feel secure. And so just to summarize, the digital certificate is to identify you, it's to stop forgery, it's been verified and authorized, and it's to show that you can be trusted. And it contains all of those things I just mentioned. It's just evidence really of a trusted organisation. So that's the sort of thing you need to write about, the need for these certificates in order to show that you can be trusted. I mean, you don't always need these. It depends on the type of web server that you have. And I would say that completes the revision for computing fundamentals. Of course, you do need to read into each of these topic areas and practice with all of the practical aspects. But I wish you luck with that, and I hope this has been helpful, at least